Hello guys, welcome to my channel. Today my topic is about angular momentum operator. In quantum mechanics, the angular momentum operator is one of several related operators analogous to classical angular momentum. The angular momentum operator plays a central role in the theory of atomic and molecular physics and other quantum problems involving rationalized symmetry. Such as operator is applied to a mathematical representation of the physical state of a system and yields an angular momentum value if the state has a definite value for it. In both classical and quantum mechanical systems, angular momentum together with linear momentum and energy is one of the three fundamental properties of motion. There are several angular momentum operators. Total angular momentum, usually denoted J. Orbital angular momentum, usually denoted L. And spin angular momentum, spin for short, usually denote S. The term angular momentum operator can confusedly refer to either the total or the orbital angular momentum. Total angular momentum is always conserved. See Noether's theorem. In quantum mechanics, angular momentum can refer to one of three different but related things. Orbital angular momentum. The classical definition of angular momentum is L is equal R multiply P. The quantum mechanical counterparts of these objects share the same relationship. Where R is the quantum position operator, P is the quantum momentum operator, multiplies cross product, and L is the orbital angular momentum operator. L, just like P and R, is a vector operator, a vector whose components are operators. Example: L is equal bracket Lx, Ly, and Lz, where Lx, Ly, and Lz are three different quantum mechanical operators. In the specific case of a single particle with no electric charge and no spin, the orbital angular momentum operator can be written in the position basis as spin angular momentum. There is another type of angular momentum called spin angular momentum, more often shortened to spin, represented by the spin operator S is equal Sx, Sy, Sz. Spin is often depicted as a particle laterally spinning around an axis, but this is only a metaphor. The closest classical analog is based on wave circulation. All elementary particles have a characteristic spin. Scalar bosons have zero spin. For example, electrons always have spin 1 by 2, while photons always have spin 1 details below.